Okay, so this is part 2 of integration and probability. Just as a quick refresher, a probability density function, a continuous probability density function, is a function for which the function value itself is always non-negative. And when we look at the integral from negative infinity to infinity, we get 1, which really represents, in sort of the discrete analog, if you add up all of the probabilities, you get 100%. That's the equivalent of that. When we want to find the probability of some range of values for one of these continuous probability density functions, we do an integral. So for instance, let's suppose that f of x is the probability density function for a person's height. Okay, that's a continuous probability density function because I could be 6 foot 1 inches exactly, or 6 foot 1.24 inches, or 6.125 inches, or 6.1245. You know, we have a continuous range of values that we can have. If I want to know that the probability, what the probability is that someone is between, let's say 5 foot 6 inches and 7 feet tall. That's not very. 6 feet tall, 72 inches. Then we would look at the integral from 66 to 72 of f of x dx. Okay, so that's how that works. We're going to wrap up this discussion with a presentation of the normal distribution. We're going to look at the normal distribution here. The normal distribution, you can take a look at this pretty curve. You hear everyone saying, hey, is there going to be a curve on this exam? And I really don't think students want us to do that, because then we'll push some scores that near the top towards the middle. The normal distribution has a mean value of mu. Okay, so we learned about mean values before. Mu is going to be smack dab in the middle here. Now, we talked about sort of the middle value in part 1 of the video. The middle value, the value where 50% of the distribution is to the left and 50% of the distribution to the right, that's also known as the median. And so this is a particular instance when the mean and the median are equal to each other. Okay, with normal distributions, and actually with any distribution, we can talk about something that's known as the standard deviation. The standard deviation is a measure of the spread of scores. And with the normal distribution, when we have a standard deviation of sigma, which we have listed up here, it's kind of easy to spot. If you'll notice, look at this dotted line here. Before the dotted line, we are concave up. After that dotted line, we're concave down until we go past the mean to the next dotted line after the mean, in which we're concave up once again. Okay, so those 2 points are points of inflection. Mu, sigma, as I mentioned before, is a measure of how far apart the normal distribution is spread. If sigma is big, that means there's a great variety in the scores. If sigma is small, then that means the scores are more bunched together. Where is sigma in this picture? Sigma is the distance between mu and that point of inflection. So this would be mu minus sigma. This would be mu plus sigma here. And I've marked off the graph in steps of size sigma, so this would be mu plus 2 sigma, mu plus 3 sigma, and then mu minus 2 sigma, mu minus 3 sigma. Now, why do I stop at 3 sigma? Well, you can see that the distribution is now very, very close to the x-axis. In fact, there is something that's sometimes known as the 68, 95, 99.7 rule, which says that 68% of the scores are trapped between 1 standard deviation below the mean and 1 standard deviation above the mean. Then where does the 95 come in? Well, 95% of the scores then are trapped from 2 standard deviations below to 2 standard deviations above. And you've guessed it, 99.7% of the scores are from 3 standard deviations below to 3 standard deviations above the mean. So 99.7 is nearly all of it. Only 0.3% of the scores, approximately, are 3 standard deviations away from the mean or more. We're going to have to, now, we haven't even discussed the function. Look at this function. There's an e. I recognize the e. Woo! Okay, e is raised to the negative of x minus mu quantity squared. So we're going to take the mean and subtract it from x. And what that does is it relocates the normal distribution. If mu was zero, then the mean would be 0. And the y-axis would be right in the center there. So we take mu minus sigma to recenter it so that we're at, or I'm sorry, x minus mu. We do that so we're centered at mu, and we square it, and then we divide by 2 sigma squared. What a crazy distribution here. And then out in front, in order to keep this to be a probability density function so that the area is 1, we have 1 divided by sigma times the square root of 2 pi. Okay? Now, that's a lot to remember. Your professor may or may not ask you to remember it. And we're also going to need technology in order to evaluate such integrals. And the reason we need technology is because this is not a function that has a standard antiderivative in terms of our basic functions. So here I have an example. It's not really example 4. So you can, well, it is kind of example 4, but example 1 for this video. The EPA estimates that the mean mileage for a group of cars tested is 24.8 miles per gallon with a standard deviation of 6.2 miles per gallon. Now, we're going to make one rather crucial assumption here. We're going to assume that the distribution is normal. Now, there is nothing that tells me this, but we're just going to go ahead and make that assumption. Sometimes that's okay to make because it may not be normal, it may be close to normal. Sometimes that's a very bad assumption to make, but we're just going to go ahead and assume that. Okay, so the mean mileage is 24.8. So I have here my standard distribution, normal distribution. And this says the standard deviation is 6.2 miles per gallon. So what we'll do is we'll add 6.2 to get to this next one, 6.2. 24.8 plus 6.2 is going to be 31. And then if I add 6.2 again, that will be at 37.2. Add 6.2 again, we end up with 43.4. And now if I start subtracting 6.2 from 24.8, that would be 18.6. And then subtract 6.2 again, we get 12.4. Subtract 6.2, we get 6.2. Okay, so that's where these different scores lie. And so we want to know what's the probability that the fuel efficiency of a randomly selected car is between 20 and 22 miles per gallon. Well, that is going to be just a very thin range. Let's see, 20 is about right here. 22 is maybe about there. So we're just looking at the region under that particular thing. So what is that particular area? Well, the probability, we use integrals. So this is going to be the integral from 20 to 22. And then we've got to use that crazy formula. So it was 1 divided by sigma. Our sigma is 6.2, multiplied by the square root of 2 pi. And then it's multiplied by e to the negative x minus mu. Our mu is 24.8, and we're going to square that, and then we divide by 2 times sigma squared, 6.2 squared. How awful. Okay, so as I said before, we need to use some sort of technology in order to come up with the value here. I'm going to use, if you're not familiar with it, you can go to Desmos.com, and they, under the graphing features, you can actually put integrals in. And we get the answer of 0.1064, which is 10.64%. For our final example, we want to look at the probability that the fuel efficiency of a randomly selected car is at least 30 miles per gallon. So I'm going to color this one in green this time. So 30 miles per gallon would be somewhere starting around in here, and it would be all the way out to infinity. Okay, we could have a car that is extraordinarily inefficient fuel-wise, and maybe it's 100 miles per 100, oh, that would be really good, I'm sorry. Really good efficiency, 100 miles per gallon. That would be wonderful. Okay, so the way we would set this up is we would do the integral from 30 to infinity of our function. I'm not going to write it right now. Well, that seems rather awful, doesn't it? 30 to infinity, that seems to be really hard to do. And since we're using technology, we can't really do 30 to infinity for one of these things. So here's what I propose. And this isn't going to work for us either. If you remember the wait time example from the previous video, if you watched that, we said the probability that we wait at least 10 minutes would be 1 minus the probability that we wait less than 10 minutes. So this will be 1 minus the probability that the fuel efficiency is less than 30. Now, technically, yes, we could go from 0 to 30 of our function. But in reality, and this is where we're not really dealing with reality, we could actually have negative mileages if we're using the standard norm or the normal distribution. So I'm going to propose something different just to give you a little bit of thinking, or a little bit of problem solving capabilities with this. So here's what I propose that we do. Let's think about this part of the graph. That is 50% of the scores, right? Okay, 50% of the data is going to be to the left of the mean. We want to know the green portion. Okay, so let's put this all together. The yellow portion that I'm shading in here, together with the red and the green, will be equal to the entire region. And we want to know the green portion. So the green portion, yes, I'm writing the colors, plus the yellow portion, plus the red portion, should equal 1. Okay, the green portion is what we're looking for. And I'm just going to do it symbolically here. The integral from 30 to infinity. The yellow portion is the integral from 24.8 to 30. And the red portion, I'm not even going to write it as an integral. I just know that's equal to 1/2. And that's equal to 1. Now, if we do a little bit of algebra, we can subtract 1/2 from both sides. When we subtract 1/2 from both sides, we end up with the integral from 30 to infinity. I'm going to leave a little space here, is 1/2. 1 minus 1/2 will give me 1/2. And I'm also going to solve for what I'm looking for. I'm looking for the integral from 30 to infinity. So we solve for that. So if we subtract the integral from 24.8 to 30, that should give us what we're looking for. So let's look at this again. I know that this particular region here should be half of the total amount. And that's kind of what we're looking at down here in this equation. I want only the green portion, so I'm going to take half minus the yellow portion. And the yellow portion I can do, so 1/2 we'll write as 0.5, and then we're going to subtract the integral there. Well, we're going to consult our technology. The integral is equal to about 0.2992, which will give us an answer of 0.2008. So a 20.8%, 0.08% chance, that should say 20.08% chance of it being at least 30 miles per gallon.